All right, so now we're going to be jumping into what most students find to be a little more challenging than the lump sum calculations, and that's annuities. And so hopefully this lecture is going to kind of get you there. It's going to help you see them for what they are and especially visualize what annuities are. I think that's really the most important thing. Because there are different types of annuities. There's present value annuities, future value annuities, annuities due, all these kinds of things, deferred annuities. And so we're going to kind of try to do our best to walk through this carefully. So let's kind of start with an overview. So first of all, there are two general types of annuities. First, there's what's called an ordinary annuity. And ordinary annuities are payments at the end of each period. So if we think about like a 3-year annuity, an ordinary annuity is one where the first payment happens at the end of the first year, the second payment happens at the end of the second year, and then the third payment happens at the end of the third year. And so that is a 3-year ordinary annuity. It's 3 years because there are 3 payments, and it's ordinary because the payments happen at the end of each period. And then there's what's called an annuity due. An annuity due is where the payment happens at the beginning of each period. So it'd be like the beginning of period 1, the beginning of period 2, and the beginning of period 3. Again, it's important to note that it would be a 3-year annuity due, meaning there are 3 payments, which is very important, but each payment happens at the beginning of each period. And so hopefully you can see that the ordinary annuity and the annuity due, they have the same amount of payments. Each of them has 3, but the timing is different. And since the timing is different, the value is going to be different, of course, because having a payment happen right now is more valuable than having a payment happen at the end of a year or at the end of 2 years or whatever it might be. And so there's a difference in the value because there's a difference in the timing. And so let's kind of walk through how that might look. All right, so it's kind of look at that $10,000 per year and sort of how that looks a little bit different. So again, let's start with the ordinary annuity. With the ordinary annuity, you can see that, it happens at the end of year 1, right here. Oops, sorry, if I could circle it, at the end of year 2, and then at the end of year 3. It's 3 payments, and each one happens at the end of each year. And then with an annuity due, there's still 3 payments, 1, 2, 3. But notice that it happens at the beginning of year 1, the beginning of year 2, and the beginning of year 3. If the first year is the yellow, the second year is the green, and the third year is the blue, you can see there's a timing. And specifically, the timing is there's a difference in value when you talk about $10,000 today versus really what ends up being $10,000 at the end of the period or at the end of the 3 years. And so, there's overlap in the middle, but the tail ends are very different depending on whether it's an annuity due or an ordinary annuity. And so hopefully this kind of illustrates the difference in the timing. And since there's a difference in the timing, there's a difference in the calculation. It's very important when it comes to annuities that you map them out. So a lot of students will draw a timeline even on the test. I think that's a great strategy. But kind of drawing it out and mapping things out and seeing where they are in time can sometimes help you see whether it's an annuity due or an ordinary annuity. And we're going to eventually introduce you to a deferred annuity. Just checking on the time, make sure we don't go too long. Anyway, all right, so let's talk about the future value of an ordinary annuity. So let's kind of start with that calculation. So again, ordinary annuity means the payments are happening at the end of each period. And future value means we want to know what it's worth or what the value is at the end, not today, but at the end. And so let's kind of walk ourselves through that. So let's illustrate it. Let me fix this. I always forget to do that. My bad. Okay. All right. So how much cash will Ford Company accumulate at the end of 3 years if it receives a 3-year ordinary annuity with payments of $10,000 that are invested at 10% APR? Again, similar information to what we've been using, but now instead of a lump sum, it's an annuity, meaning that there are now 3 payments, not just 1. And so let's kind of take a look at this. Just again, thinking through it mathematically, at the end of year 1, you're going to have $10,000, right? Your first payment at the end of year 1. At the end of year 2, if you remember the last time, we talked about basically just these first 2 terms. You have the original principal, and then you have interest on that amount. But in this case, now we're introducing a second amount, which is that second payment. So now there's a second payment. But notice now at the end of year 2, I actually have $21,000. I have the $10,000 plus another $10,000 plus $1,000 interest. And so at the end of year 3, I've got the $21,000 that I had at the end of year 2. I have the interest on that $21,000, and I have one more payment of $10,000 for a total of $33,100. So that's, in a picture, what's happening, right? And so if we kind of visualize it in terms of what we kind of started with, you can see that today there was nothing, right? We didn't start with anything anywhere. We're just sort of growing based on these annuities. And then we have a cash flow at the end of year 1. That's for this first 10,000. That 10,000 keeps growing by itself. If you're going to kind of think about it that way, the 10,000 grows to 11,000 and then to 12,100. And then we have a second $10,000, but it only grows for 1 year. It only has interest for 1 year, so it grows to 11,000. And then finally, we have the last payment of $10,000. And because we are calculating the value at the end of year 3, there's no interest on that 10,000. We add it all up and we get $33,100, again, using a 10% interest rate and 3 annual period payments. All right, so hopefully, again, that picture helps you see how an ordinary annuity works. Let's kind of do some calculations. So let's talk about the equation approach for the FVA. When you see FVA, what it means is fair value of an ordinary annuity. Fair value of an ordinary annuity. So we're going to do a little bit of algebra. Again, the fair value of an ordinary annuity, we're just kind of mathematically illustrating what we already knew. So that first $10,000 payment at the end of year 1, it accrues interest 2 periods. The second $10,000 payment accrues interest only 1 period, and the third interest payment doesn't accrue any interest. And so we're just kind of illustrating that. So what do? Well, we can factor out $10,000. So the $10,000 here, here, and here. We factor that out, and basically we have now 3 terms inside this bracket. 1 plus the interest rate times itself, and then 1 plus the interest rate by itself, and then just a 1, right? So we're just factoring out the $10,000. So what do we do then? You can see that this first term is 1 plus the interest rate squared. The second term is to the first power. And if I want to rewrite 1, we know that we can take anything, any amount or any term, and if we put it to the 0 power, it equals 1. So I'm just rewriting it this way, and you're going to see why in a second. But essentially now I have $10,000 as a basis, and then I have this progression, right? I have a squared term, a singular term, and then a term to the 0th power. All right, now here's where it gets a little complicated. And by the way, not on the test. As far as doing the math, I want you to understand the concept. And the reason why I want you to understand the concept is because you're at a point, hopefully, where you want to be more of a professional accountant or finance person, and you need to understand the math behind what you're doing. I'm not saying you need to be able to always do the math, but you need to be able to comprehend it. And so what annuities rely on, any annuity calculation relies on this thing called a geometric progression. And a geometric progression is a way of solving this sort of where you go from a squared term to a singular term to a 0 term, because it's very difficult to solve otherwise. And so let's kind of look at this. And so if I rearrange the terms, my fair value of an ordinary annuity, basically, kind of thinking about what do I have? I have a $10,000 times something to the 0 power, the same $10,000 to the first power, and the same $10,000 squared. And so you can see that this term is being progressed from 0, 1, 2 as far as its power. To simplify what we call a geometric progression, again, that is what a geometric progression is. So when you have a term that is going to the 0 power, then to the first power, squared, cubed, on and on we can go. All right. So the way we solve for a geometric progression is that we multiply both sides by the progressing term. So we're going to multiply both sides. And again, the term that's being progressed is 1 plus 0.1. That is the term inside the parentheses. That is the term that is being progressed. So we essentially write a new equation. Now, when I multiply both sides by 1.01 or 1.1, I'm doing nothing to change the equality. It's still equal. but now we have this interesting situation where on the left-hand side, we have 1 plus 0.1. And now instead of being 0, 1, 2, we have 1, 2, 3. So now we have this progression. Instead of being 0, 1, 2, the progression is 1, 2, 3. And then what we do from there is we subtract the first equation from the new equation. So this is where it gets a little heady. Don't get mad. Again, not on the test, but for some of you that want to geek out a little bit, hopefully this is an interesting process. Because for me, I wanted to know where these numbers come from. Again, you're gonna see at the end of the day why this becomes important, but I wanted to kind of show you how this all works. All right, so now on the left-hand side, if I just subtract these two equations from each other, they're the same thing, right? If I have, A equals B, C equals D, A minus C equals B minus D is essentially what we're doing. And so, it's just a mathematical truth. And so what we do is we rearrange these terms. And essentially we have the first equation being subtracted from the second equation. So we see that the left-hand side of the first equation is here, and then the left-hand side of the second equation is here. And what's interesting is what you have in the middle are some common terms. And so you see 10,000 times 1 plus 1 to the first power is both in the the new equation and also in the first equation. And the same is true for the squared term. It's in the new equation and it's also in the first equation. Those things cancel out. So as they all cancel out, our equation becomes much simpler. So let's look at it. So when we simplify it, the only thing that's on the left-hand side is, if I go back a little bit, sorry, that was a little bit of a jump ahead. Oops, sorry. The left-hand side, we have the FVA, right, is in both terms, right? And on the right-hand side, the only thing we have is 10,000 times 1 plus 1 cubed, and 10,000 essentially times 1. This second term is times 1. And so when we simplify it, that's all we're doing. We're pulling the FVA out. And so the first term is 1 plus 1. The second term is just 1. And we're pulling the 10,000 out. We're kind of like looking at this on the right-hand side, which is this second step. So now the 10,000 is over here, and we have our two terms left on the right-hand side. And if I kind of simplify this information inside of here, 1 minus 1 equals 0, and we're left with the interest rate, 0.1. Again, try not to get too beat up, but essentially then, if I want to move things over, I divide both sides by the interest rate. And so notice now I have an equation. I have the annuity amount, I have the interest rate, I have the N, and then I have the interest rate again. So now I have what's called a general form equation. And so, but again, I can solve for that and I get the future value, same number, 33,100. So when I solve for that, but I want to kind of show you the general form equation. So if I take that 10,000 out, the payment, the annuity kind of sits by itself. This is everything that's left. This is very important. This ends up being the factor. If I can do it, right? So the FVA factor. So that is the FVA factor. So when we see a factor table and we wonder where did those numbers come from, it's right here. This is where those factors come from. 1 plus I to the nth minus 1 divided by I. That is where the factors come from. And so while you can use this equation, right? I could use this equation. If I want to solve for the future value of an annuity, I can take my payment, I can take my I, I can take my N, and I can solve. On the test, you do not have to do that. But I wanted you to understand now when I use the tables, where did those factors come from? And it comes from this term right here. And so now as we fast forward to the tables approach, again, we're taking that general form, and that second term is the FVA factor. We apply it to our situation, and we can see that the factor should be 3.310. Given an interest rate of 10% and an N of 3, if we're looking for the future value of an ordinary annuity, this is the factor that we should observe. And so when we do that, again, that's the factor that we're looking for for this scenario. Let's see if it's true. So we can see that 10%, cross it with 3 as our n, and you can see that is our factor. Again, the equation allows us to see where these factors come from. But again, on the test, you are not going to have to use that equation. I just wanted to just see sort of how we got to this table, these table amounts. All right, so then we have, again, for this example, the factor would be 3.31. The way you apply a factor is you multiply it by the base. In this case, the annuity was $10,000. We apply that factor, and we get $33,100. For a second example, let's see if you can do this on your own. So again, pause it here, see if you can do this one on your own, and then we'll pick it back up and see if we can solve it together. So again, using the factor table, what is the future value of a 7-year ordinary annuity if it can earn 8% annual interest? Again, we are not going to use the equation, although we could. We're going to use the factor table. And so again, 7 years at 8%. And so we're looking at 7 years and 8%. So if we're looking at this intersection, we got our 7 years and we have our 8%. And again, hopefully you have a sense of where that number came from. So our number is 8.9228. And again, it's compounding, that's more payments, and that's why the factor goes up. So, compounding more periods, more payments means the factor needs to go up. So looking at this, we apply it. So the factor is 8.9228. We apply it to our annuity amount of $2,000, and we get $17,845.60. So that $2,000 will become $17,845.60 after 7 years of earning 8% annual interest. Again, that's how we use a table. And then finally, and you're going to see where this is where it starts to get I think where the calculator really starts to show its worth is, how much cash will 49er Company accumulate at the end of 3 years if it receives 3-year ordinary annuity with payments of $10,000? Again, we know the answer. But let's put it into our calculator. Again, in this case, we are solving for a future value. We want to know how much it will be in the account at the end, but we have to fill in the rest of the information. The end is still 3, that hasn't changed. The interest rate is 10, that hasn't changed. There is no initial lump sum. If you remember that picture, initially there's nothing in the account. But at the end of 1 year, there will be. And as I invest, that's kind of money coming out of my pocket. And then I'm wondering, how much can I take back at the end of the 3 years? Well, the answer is, when I compute the future value, the answer is $33,100. Again, hopefully that makes sense. So in the second example, again, fill it, pause it here, see if you can do this on your own. Again, we have a $2,000 annuity, 7 years, 8%. You should be able to fill everything in and solve for that future value. So solve it, pause the lecture, solve it on your own, and we'll see what we can see if you get the same answer. And again, the answer should be $17,845, and we get slightly different because of rounding, 61 cents. But again, n is 7, I/y is 8. There is no lump sum initially, and then it's a $2,000 payment. All right, so we are going to stop there, and next time we will pick up with the future value of an annuity due.